Okay, so now let's think about a different example of a situation with cylindrical symmetry. We're going to have a cylindrical shell of charge. So this is a thin cylindrical shell that's infinitely long, so it extends infinitely in this direction, but it's hollow. So there's charge on this outer surface, but it's not a solid cylinder, it's just a hollow shell. And I'm going to ask two questions. One, what is the electric field at some point here outside the shell? And two, what's the electric field at some point here inside the shell? And I want both of them to be at some variable radius, little r, away from the axis of symmetry. So we'll use our multi-step procedure again. It's fairly clear that the electric field outside the shell has to be radial. So that's step one, is guessing what the electric field has, the form of the electric field. Inside the shell, it's not so obvious whether the electric field would point radially inward or radially outward, but it has to be radial because of the symmetry of the situation. Step two, cleverly choose our Gaussian surface. So we're going to choose the same surface as we did before because the situation has the same symmetry as it did before. Oh, by the way, I should say, let's say that our shell, our spherical or cylindrical shell, has a radius of capital R. So again, we'll choose a cylinder. So there's the curved outer surface of the cylinder that we're going to choose first for this outer point. And there's the top cap, and there's the bottom cap. And then we go through the steps of breaking the surface into parts and evaluating the flux. All of that works exactly the same as it did before. So just as before, we have to assign a length L to our cylinder, and the flux is going to work out to be the electric field at the surface of the cylinder, which is our desired unknown, times the surface area of the cylinder, which is 2 pi RL, just as it did before. Now this is for outside. Now let's think about inside. So for inside, I also choose a cylinder. The cylinder has to include this point inside that I want to find the field at. So this is going to be a cylinder again of, I'll define the length of my cylinder to be L. And I work out the flux. Now in this case, I don't know whether the flux is pointing outward or inward. I'm going to define an outward pointing electric field to be positive. With that definition, all the steps are exactly the same. I break this up into different pieces. The electric field, if I define it positive, outward, is parallel to d vector A on the curved surface, perpendicular on the flat surfaces. So inside, we get exactly the same result. Phi sub E equals E times 2 pi RL. If it winds up that we have a negative value of the flux, that means that the electric field is actually pointing inward. If we get a positive value of the flux, the electric field points outward. The next step is to find the net enclosed charge. So net enclosed charge outside, it's very similar to what we had before. Let's say that the cylinder, the cylindrical shell, has charge per unit length of lambda. So that is, for each meter of the cylindrical shell, there's lambda times 1 meter worth of charge spread over the surface of the charge. So outside the shell, the enclosed charge is lambda times L as before. Inside the shell, there's no enclosed charge, so there's no charge enclosed by this smaller cylinder, so it would be 0. And in the final step, we use Gauss's law to find the field. So finding E, outside, we set the flux, E 2 pi RL, equal to the net enclosed charge, lambda L over epsilon naught, because it's Q net enclosed divided by epsilon naught. We cancel the factors of L, and we solve for the electric field. E equals lambda over epsilon naught 2 pi r, just as we had before for the narrow rod. And this is independent of the radius capital R of our shell here. So it's quite an important result. For a situation of cylindrical symmetry, the electric field outside is the same as if all of the charge were collapsed to the inside. And in the book they go through that is collapsed down to the central axis. In the book they go through a similar argument for a case of spherical symmetry, that if you have a situation of a spherical shell, the electric field outside the spherical shell is the same as if all the charge on that spherical shell were collapsed down to a point at the center. What about inside? Inside, we have the same expression for the flux, E 2 pi r L equals 0, because there's no enclosed charge, and so that means that the electric field is equal to 0 inside. So, and again, it doesn't matter what the radius of the cylindrical shell is. Once you're inside of it, the electric field due to it is the net electric field due to the entire shell is 0. That's a little bit hard to accept for many people when they're encountering that for the first time. Let me give you a little bit of a way to understand that. In a top view, here's our cylindrical shell with the charge spread uniformly above it. And what we're saying is any point inside the shell, the electric field is 0. Well, how can that be? How can it be that at the center it's kind of obvious that it's 0 because of the symmetry of the situation? This side is has an electric field that points down, this side has an electric field that points up, they cancel out. But over here you would think, oh, I'm closer to this charge than to this charge, and so how can there be cancellation? Well, one way of seeing that is that if you look with a field of vision of, let's say, a 90-degree field of vision this direction, then you can see sort of this amount of the cylindrical shell. If you look with that same field of vision in this direction, you see a larger amount of the shell. This part of the shell is creating an electric field that would point to the left. This part is creating an electric field that would point to the right. This part is farther away, but there's more of it, and those two effects exactly cancel out so that you get 0 net field at this point. So putting this all together, you get a very, very important conclusion. For spherical or cylindrical symmetry, so I can make up any, so I'm going to finish this sentence, but I need to say something a little bit more first. Let's say I've got a complicated charge distribution that has cylindrical symmetry. So here's a shell that's got some positive charge on it, and maybe that's surrounded by a thick shell like this, and the thick shell has some negative charge distributed through its thickness, etc. So there's some complicated charge distribution, and I want to find out, and all of these are infinitely long, these cylinders. I want to find out what's the total electric field due to all of them as a function of the radius away from the center. So perhaps I'm at some radius where I'm in between the green and the purple. I draw a Gaussian surface at my radius of interest. Any charge that's outside that surface will contribute no electric flux by the arguments that we just made for this smaller cylinder here. And any charge that's inside my blue surface will produce an electric flux that's the same as if all the charge were concentrated at the center, along the central line. So to finish my sentence, for spherical or cylindrical symmetry, the electric field at radius capital R is the same as if all the charge at radius little r less than capital R were concentrated at the center, and by that word center, in the case of cylindrical symmetry, I mean concentrated down to the center line. In the case of spherical symmetry, I mean concentrated down to the center point at the center of the sphere. And all the charge at radius little r greater than capital R didn't exist. Because we saw that, let's say for this small blue cylinder, the charge that was outside of it didn't contribute any net electric field. So once, if you're in a situation of cylindrical or spherical symmetry, once you get inside some radius of charge, that charge doesn't contribute any net electric field. So this is a very, very important principle that you will make use of many times during this course, and that certainly deserves a 2-star box. I'm going to pause here and we'll pick it up in the next segment.